Here we have Euler's equation. Okay, this can be represented as a vector of a unit vector, so its length is 1 in the real imaginary plane. So we have a unit circle that's drawn in the real imaginary plane. So right here, this would have a value of 1, 0 up here. Since this is the imaginary plane, is 0, I up there. Okay. So at 0 radians or degrees, you're all real. 100%, that 1 is 100% real. At 90 degrees or pi over 2, so pi over 2 is up here. Okay. The Euler's equation would have a value of I because it's completely imaginary. So let me just generically draw in a vector at an angle of theta to be represented by Euler's, or to represent visually Euler's equation. Okay. So if you were to look at that, the adjacent side would be the horizontal component. Okay, would be given by the hypotenuse 1 times the cosine of theta, and the vertical side could be found using the sine of theta. All right. So the horizontal side tells you how much you're in the real direction, and the vertical side tells you how much you're in the imaginary direction. Now, if I were to look at e to the negative I theta, okay, visually that would be the same as going negative theta. So my picture is a little bit off. It's not completely symmetric. Okay, but I would go theta in the opposite direction. All right, and you can see the x component is the same. So that would still be the cosine of theta for its real part or horizontal part. And the vertical part, though, would be the negative of I sine theta. Okay, it's a congruent triangle down there, so its vertical size is still given by sine theta, but it's in the opposite direction. So that would be that location there. Okay, so now if we look at those equations, okay, we can see that we might be able to relate that to what a cosine or a sine is. Okay, so the first thing we can do is we could add the two equations. If we add them up, all right, we can see that e to the I theta plus e to the negative I theta would end up being 2 cosine theta, and the sine theta parts would cancel out. Okay, so that tells me if I divide both sides by 2, I can say that the cosine of theta is equal to e to the I theta plus e to the negative I theta over 2. All right. Now, if instead we had subtracted, I'll switch colors here, and we wanted to do e to the negative, to the I theta, oops, not negative, minus e to the negative I theta. When we look at the right-hand sides, we can see that the cosines would cancel, and we would end up with 2I sine theta if we add them. Therefore, we can say that the sine of theta is equal to e to the I theta minus e to the negative I theta all over 2I. Okay, so these two equations we can define sine and cosine in terms of Euler's equations. Okay, and so we can rewrite them. Now, that's very important as we do the harmonic oscillator, because we said that the solution, go back to white here, was A1e to the, let's see, what was this? I'm sorry, as a solution with e to the negative gamma t part, right? Times A1 e to the I omega t, all right, plus a2 times e to the negative I omega t. So we had determined that that was our solution. All right. And then it was stated that magically, with Euler's equation, we could say that it was really equal to e to the negative gamma t times c1 cosine omega t plus c2 sine omega t. Okay, so we need to show that those are actually equivalent expressions. And we might also see why we want to use the cosine and sine version instead. Okay, so first of all, if we look at the two of these, okay, we can see that the decay part is the same. Okay, so we need to show that C1 cosine omega t plus C2 sine omega t could be rewritten in terms of these imaginary exponential expressions, okay? Or vice versa, we could take the imaginary exponential. So we could start here and show that we can get up to here, or the other way around. I'm going to do the first thing because it's easier, okay? So if we just start with C1 cosine omega t plus C2 sine omega t, you should realize that omega t is the angle, okay? We know with an oscillator that angle is changing over time, which is why it oscillates, okay? So we could rewrite that as C1 e to the I omega t plus e to the negative I omega t all over 2 by subbing in what we just found cosine could be written as, okay, plus, and then we would get C2 e to the I omega t minus e to the I omega, oh, that's negative I omega t all over 2I. So I'm going to show that, and those things will be equal by how we define cosine and sine. All right. Now we want to do a couple little tricks here. Okay. Trick number one is, well, I'll bring the 2's out front. That's easy. Okay. But what I'm going to do is I'm going to multiply this by I over I. Okay. And I times I is -1. So bear that in mind. Okay. So what I can do is I can rewrite this as C1 over 2 times e to the I omega t plus e to the negative I omega t. That's my first term. And then I'll have minus because of the I times I in the denominator. Okay. And then I'll have I times C2 over 2 e to the I omega t minus e to the negative I omega t. All right. Okay, now let's figure out how many e to the I omega t's I have. Okay, so I have a certain number of e to the I omega t's, and I'll have a certain number of e to the negative I omega t's, right? So if I do a little distribution, I have C1 over 2 of the e to the I omega t's, and then I have a minus I C2 over 2 times the same thing. So let me write those in here. C1 over 2 minus I times C2 over 2, right? Now let's figure out the other, how many of the e to the negative I omega t's I have. Okay, so I'll put plus there, and I have, once again, I have C1 over 2 of them from the first term, and from the second term I have a double negative, so it will be plus I C2 over 2. Okay, so we can see with our string of equalities here, we started with C1 cosine omega t plus C2 sine omega t, and we were able to get to a series of constants. So this would be my A1, and this will be my A2 times e to the I omega t and e to the negative I omega t. All right. Now, these constants aren't as nice to work with. This is a complex number. Okay, it has a real part and an imaginary part. And this is a complex number. It has a real part and an imaginary part. Whereas if we start with C1 and C2, those will be real numbers. Okay, they're not complex at all. So by converting our solution from the exponentials with imaginary exponents into cosines and sines, we can have real constants instead of imaginary constants. So we've shown that using Euler's equation, we could rewrite cosine and sine in a way that will let us take our solution that we had from before, that was this right here. We can take that solution and we can convert it into the second solution, which is much easier for us to work with.